Um, I will give the talk in English if that's okay with everyone. As Bülent Hoca said, I did my bachelor's degree in METÜ, and then I did my master's degree in the METÜ Institute of Marine Sciences, where I started doing hydrodynamic modeling and coupled biological modeling. And then I was accepted to PhD in France. Okay. And then I was accepted to PhD in France in a joint doctoral project with Sorbonne Universities and the Ifremer Institute, where I conducted this study. And I would like to give you a short summary of my PhD study and talk about my work. I will do the talk in 4 short parts. I will start with an introduction. Why the submesoscales? The title of my talk is the submesoscale dynamics in the Bay of Biscay. With the advancement of satellite imagery and computer power, we are able to resolve higher and higher resolutions while we are studying the ocean. And we realized that the submesoscales are an important part of the ocean dynamic. And in these regions, strong vertical currents are generated, which helps bring up nutrients to the surface where light penetrates. And also, it can change the residence time of biological organizations in the euphotic zone where light penetrates, which also affects the biology, which creates a carbon pump. And these newly resolved scales can be a key part in explaining the budget, the carbon budget, and the biological budget in the ocean system. What is a submesoscale? This diagram is very famous. It starts from the planetary scale, like the climate change, and then basin scale, sub-basin scales, all the way up to the, all the way up to the molecular scales here. So when we mean scales in the ocean, there are some numbers, unitless numbers we use to define scales. For example, first one is the Rossby deformation radius, which is the balance between the Coriolis forces and the advective forces when we look at the motion. It is skipping by itself. Sorry. When we the motions at the same scale as the Rossby deformation radius are defined as the mesoscale. Mesoscale is, for example, the eddies in the ocean, not as large as the whole basin, but a degree of magnitude smaller. Another number we use is the Richardson number, which tells us how the stratification of the ocean is affecting the motion. So is it well mixed all the way to the bottom, or is it stratified? Stratified means the top layer and the bottom layer don't mix very much. There are layers vertically. So when we define scales in the ocean, we look for Rossby deformation radius and the Richardson numbers at the magnitude of around order of magnitude of 1. So it gives us approximately here, smaller than mesoscale, but not as small as like molecular or like in your bathtub small, which is around 1 kilometer in space and around daily to weekly in time. And what are the physics? What are the dynamics we observe in these scales? First one is baroclinic instability. I'm sorry if it's too technical for who is not very familiar with this. This kind of formation is called a front. If you have like a vertical boundary in a body of water, for example, cold to hot or like salty to fresher water, if you see like a boundary, it's called a front. And when it goes under instability, because the water is not like a rigid thing, they intensify. The there are a lot of details about this, but the front gradient intensifies and they go under instability. And this is one of the dynamics we will observe. The other one is frontogenesis. It means this kind of straight front meanders like this. It creates filaments and turbulence along the boundary, and then these filaments become greater in gradient, and they create strong submesoscale velocities in this little, how to say, little turbulence-like structures. And why the Bay of Biscay? The first part was submesoscales. The second part is why I conducted this study in this region. Bay of Biscay is the Atlantic coast, this part of the French Atlantic coast. And the shelf region here is the light blue part, is a large shelf and quite flat. And there are two major rivers, Gironde and Loire. They discharge huge amounts of fresh water every winter. And there are well-defined tidal dynamics, Atlantic tidal currents. So it's basically like an ideal laboratory, like flat, large shelf. We have freshwater input, we have tidal dynamics, very well-defined currents. And we chose this area to look for these kind of dynamics. And the surface circulation is mostly poleward and wind-driven, and there are density-driven component, which is the Loire and Gironde rivers, this river mouth and this river mouth, and the tidal dynamics are semi-diurnal, very strong around the islands and the ocean region. And their seasonality is very well defined. I'm not going into very much detail. If anyone's interested, I can give you details. And the aim of this study is to identify and characterize submesoscale dynamics in this shelf region and understand the physical dynamics, like how they behave or their seasonality. And like I said, the physics involved, like the instabilities and frontal dynamics, which constitute these submesoscales. So for doing this, I first started with characterizing the frontal activity. I analyzed 11 years of satellite data from the MODIS, Aqua, and Terra satellites. This is an example from January 2008. I used around 1 kilometer ungraded level 2 data. And this is the region enclosed I analyzed. And before doing it, I have to do a quality check because it's a very cloudy region. So I eliminated more than 90% of the data. I only used this dark red bits. So these are the years, and the image quality is really, really low in most of the images. At the total, I had almost 3,000 images for 11 years. And I applied a mathematical analysis to each of the satellite images, which is called singularity exponent. It has a very complicated mathematical definition, but basically it tells you how smooth or how broken your function is over a field. So if your function is discontinuous at some regions, like a front, it will give you a signal. For example, these white regions. Yes, it's a discontinuity in your function. So here is the image, the raw image. You see there is a very strong gradient in temperature, and these white pixels tells me there is a discontinuity. The singularity exponent goes to the negative. It means my function is broken. It's not smooth around these regions. So I use this singularity exponent, And I identified a limit to what a front is. So I said between minus 0.2 and 0.6, which is basically the whitish part in this image, is a front. And I calculated with what frequency I observe a front in a given region. So I put 11 years of satellite images on top of each other. And for each pixel, I looked at how many times that pixel is flagged as a front. Out of 100 times, it gives me a percentage. So for example, this is an example of April, May, June. It's the spring month. So these greenish pixels says that 25% of the time a front occurred there. So I looked at this probability distribution for every season, and this is the flagged pixels. This red shaded parts are a front. And I came up with this seasonal distribution. There are very distinct differences between winter and summer months, and spring and autumn are the kind of transitional periods. The first thing we observed is the tidal fronts in summer months, because tides are the most dominant advective feature. And in winter months, we see the fronts very confined to the coast, dominated by freshwater input because it's the rainy season. And I went on to analyze what's going on in this region. So I utilized a model developed by Ifremer, which has a 2.5 kilometer resolution. Not good, but we will see the vertical structure, because when we look at satellite, it only gives us the surface. We don't know what's going on in the depth of these fronts. And this is the validation of the model. I don't think it's very important. And this is the same analysis done for the, did the same again, pixel by pixel probability analysis for the model outputs as well. And what I came up with, there are two major front categories in this region: tidally induced fronts and freshwater fronts. And the tidally induced fronts are around this region, which are very confined to the like bathymetric lines. Bathymetric lines are the depth contours, and around islands, and at the shaft break, which is around 2.5 250 meters depth. A shaft break is where the shaft meets the abyss, which is a sharp decline in the bathymetry. And in winter months, the fronts are confined along the 100-meter depth, following along the coast, very defined, very following the bathymetry, like so. And we wanted to see what's going on at depth. So this is my model output I used. For example, this is the tidal fronts I was talking about. And I looked at a transect along this region. So this is the temperature at the surface at that time. This is an example of a snapshot. This is not averaged or anything. And I looked at the vertical distribution. So this is a highly stratified ocean. In summer months, it gets very warm at the top. The heat doesn't penetrate at the bottom. It's very cold. But as we say the ocean breathes, as the tide comes and goes twice a day, because of the bottom friction, this part gets mixed. So we don't see the hot on the top and the cold at the bottom anymore because of the friction. That's called the tidal front. So that's what we see here is the coldish waters coming up, and these are the warmish waters. This is one type of front. And the other type we saw was at the shaft break. So Shelf break is this region. There's a sharp decline at the bathymetry, and this region is 4 kilometers deep. This region is like 250 meters deep. So what's happening here? These are, again, the stratified summer conditions. It's warm at the top, but all of a sudden it gets mixed with coincides with this shelf edge. So we looked at internal tides. Internal tides are the internal waves generated at the depth, not at the surface of the ocean. So when this is a slice of the ocean at the shelf edge from another model. It's called the internal wave model. So when the ocean like breathes twice a day, it it gets brushed against the shelf edge and it causes some waves to break inside the ocean, not at the surface. So that's why this part gets mixed and we don't see this warm surface waters anymore. And we see these little coldish waters at the shelf break, and this creates another type of front. And the third type we see in winter. Um, these are the river inputs from these two major rivers, cold waters coming in, and then they are trapped along the coast. And this is how they look along a transect. They sit on top of the salty water because they are fresh, they cannot sink, and they are cold. So this is the reverse. We have a cold front here. We have a cold water, and the the surrounding waters are warmer than the fresh water. I talk about fresh water, low salinity, but I am showing you temperature. How can this happen? So it is called it is something called differential cooling. When you put fresh water on a dense water, it cannot sink, it just sits there. And when you put negative heat flux on top, because it's winter, it cools and it cools. The surrounding waters can mix because there is no barrier. It can mix down to the bottom, but the fresh water cannot mix down to the bottom. So the top layer gets cooler and cooler. It cannot sink because it's too fresh. So river input gets colder than the surrounding waters. So that's why we can see it in the temperature satellite images. We can look at the temperature and say, this is fresh water because it cooled more than the surrounding waters. So that's another type of front we observed. And the things I told you about up to now is published in this paper in 2017. And we wanted to see how we can analyze these satellite observed fronts in a higher resolution model. So I developed my own model using the IFRA Mars 3D hydrodynamic setup. I used a 1 kilometer resolution. The previous ones I showed you was 2.5. We went very high with the resolution this time. And we used realistic inputs like river fluxes and wind and tidal forces. And I ran this model in a big computer center called Oxygen. It was the biggest in Europe at the time. And here is the region I used, the same as the satellite images. And this is the validation of the model against in situ data sets. I can give you details later. And if I did the same analysis with the frontal frequency. This is the model I showed you before, and this is the higher resolution. You see there are a lot more structures picked up by the analysis. And against the satellite images, it's much less noisy. We have a lot of noise in the satellite. And to see what's going on, we
Yeah. Did you capture the coastal shelf from Janet?
Which one?
The middle one is yours, right?
Yes.
Oh, continental shelf.
This one. Yeah, it's missing because it's nested inside a larger model, and the boundaries are damping a lot of the internal waves. We don't have a lot of the internal waves in the nested model, but we have tidal component as advection, not as waves. Yes, the slow part, yes. Yeah. But because it's an internal dynamic, those internal waves are generated like 200, 300 meters deep. It doesn't affect the surface dynamics at all. The tidal component is mostly advective in my model. In the boundaries, we give the velocity of the tidal currents in and out of the region. Mhm. Yeah, but you have to run your model at least like 10 years to reach at that level of internal wave generation. You have to have a long spin-up time to generate those waves, because boundaries dampen waves by nature. If you put a boundary in your model, because we are not modeling the whole planet, we have to put a boundary. You put boundary conditions, and boundary conditions by nature dampen unwanted waves, like a buffer zone. Mhm, mhm.
Means that some energy is being taken by these waves
Yes.
and carried away. Is this a important? Is this a significant part of the barometric energy that's
No, it's too far away from the dynamics I'm looking at, and it's too deep. Yeah. Yes, surface. Um, so to I made two axioms to diagnose what kind of dynamics we are observing. And the first axiom is the barochronic instability is the dominant process. So we will specifically look at this dynamic. So what does this mean? Uh, Positive vertical buoyancy flux is generated. What is a buoyancy flux? If you have a vertical motion, which is denoted by W, and if you have a buoyancy is basically like lightness of water or denseness of water. Uh, W is positive, it means upward, and buoyancy is positive. It means light water is going above the dense water. And buoyancy is negative, which is downward, and um, W is negative and buoyancy is negative. Their product is again positive, which means basically if you have like a vertical setup, light water on one side, dense water on the other side, they try to tilt naturally. The light water tries to go above the dense water, which creates positive WB. In either case, light water wants to go up, dense water wants to go down. In either case, it's positive WB. So I'm looking for positive WB. So I plotted it, but this is the whole thing, the whole W and the whole B buoyancy. Not everything is submesoscale. So how am I going to differentiate between different scales when I look at an image like this? So I applied something called scale decomposition. So this is my assumption. It's not like a written rule anywhere, something we devised with my advisor. So I made like a monthly average in time. So I am eliminating most of the large scale motions. I first subtracted that. And then a medium low pass filter, like weekly averaged, and then 5 point smoothed. You have a pixel and you have 4 neighboring pixels, and then I take the average of that. It's called a 5 point smoother. And I did that 8 times, and I averaged it in weekly time space. So it's the medium-sized dynamics. So I subtracted this and this, in this manner. What the remaining part is will give me the submesoscale. The single prime is mesoscale, the double prime is submesoscale. So I came up with this. This is the large scale component, bar, and this is the mesoscale component, prime, and this is the submesoscale, double prime. But since we have two terms, the product of two terms is not always the product of individual terms. It's a 9-term addition. There are some terms which are non-negligible. For example, I did something. The large scale vertical motions and mesoscale buoyancy are not negligible. I computed all of these terms. I omitted the negligible ones and I subtracted them from the total to come up with this prime and prime term. This is called a scale decomposition. And my second axiom is when you have the setup I just described a minute ago, when you have a light water and a dense water side by side, it has a lot of potential energy to stay like that vertical. So when it tries to tilt, this potential energy is released as kinetic energy. And the rate at which this kinetic energy is released is can be not equal, but they are of the same magnitude as this vertical buoyancy flux. So we can look at time scales of how this energy is released and come up with a number, and then the process, the fastness of this process will tell us if it's a submesoscale process or it's a slow process. So I did this with these two axioms. So I looked at the summer months and the winter months because that was what I observed in the satellite images. So here is the eddy kinetic energy released in summer months, and here is the vertical buoyancy flux. Just as like the satellite images, we have very significant submesoscale vertical fluxes here and energy released around the same regions. Again, I don't have it around the shelf. I just have it around the geographical features. And in winter, like I said, the shelf is very active, very strong vertical dynamics, and very much energy released around the river plumes. And when I look at the average of time, how this energy is released, in winter it's around 1 day, and in summer it's around 3 days. So it's basically submesoscale. It's a very fast process. And I will give you two examples of a daily snapshot, how this is observed in the model. And this is from the summer months, the model outputs. This is the eddy kinetic energy, and this is the buoyancy flux, and this is the temperature. So we see the front here, and here, consecutive fronts, and the kinetic energy released perfectly coincides where the front is. Again, at the vertical buoyancy, the vertical dynamics, these red blobs are positive buoyancy, coincides perfectly where the front is. And this is the view on top. This is where my front is. And there are smaller fronts inwards here. So this is just like a confirmation of what I showed like in the previous slide. And one example from winter. Here, I have the salinity transect along this line. This bluish color is my river plume. Here I see it in salinity, consecutive fronts, smaller fronts, and this is the huge front here. And it coincides with this kinetic energy release, and it coincides with this reddish vertical upward motion. And there are other dynamics which can define if your motion is submesoscale or not. One of them is called the slope Berger number. In Hetland's paper, they define the slope Berger number should be smaller than 0.2 if your motion can be characterized as submesoscale. And it is defined with terms like the slope under your front and the horizontal gradients and other parameters. And I applied that to my region to see if it really checks out. And slope Berger number for this given front is 10 to the minus 2, well below 0.2. So it checks out. It is confirmed that I can capture submesoscale dynamics in my region. So in the beginning, I listed my objectives as like identifying this kind of fronts in this region and understanding their physical dynamics. And in the last step, I investigated the baroclinic instability to see if I can capture that with my model. And I looked at the time scales and release of eddy kinetic energy, and it is confirmed that this region is producing these fronts. And I would like to finish with this image because it's a very nice way of showing why are we doing this. This is a snapshot of chlorophyll from the same region, the biological activity. And I put on top of it, these black structures are the singularity exponents, the frontal pixels I defined to see how good they match. As you see, where there is a front, there is biological activity captured by the same satellite. So it is a good indicator of these small scales contributing to the vertical motions and the ecological activity. And what else can we do with this kind of information? In most of the models, they resolve mesoscales and stop there. They don't go that far because of computer capacity is very limited, measurements and instrumentation is very limited. So there is this gap in the budget. So maybe this kind of small filaments, etc., are not negligible. They should be resolved to fully understand the climate dynamics, the other important parts of these models, or maybe atmosphere ocean interactions. So that's why it's a good addition to go forward in the hydrodynamic modeling. I think that's all. Yes. Thank you.